All right, so I told you eigenvalues and eigenvectors are awesome, amazing, and useful. So how do you find the stinking things? All right, well, we're going to use a basic idea in math that's super common. It's sort of a meta idea for how to solve things. If you want to solve a equals b, turns out that solving a minus b equals 0 is often easier, just because it allows you to work with 0. Makes it possible to do things with absolute values. You can do estimates. You can do all kinds of other things. In our case, it will allow us to turn a matrix equation into a numerical equation. So here's the idea. Oh, and I should just back up here a little moment and mention that I started off talking about eigenvectors and eigenvalues of linear transformations. So where we have some general L right here. In this class, we will concern ourselves primarily by what am I doing? Sorry, that's supposed to be next. Looking at the case where L is multiplication by a matrix. Okay, so we're going to be solving this equation right here. AX equals lambda x. All right, so first off, note that AX equals lambda x. This is, well, I want to use that trick that I wrote over at the side by looking at a difference. But if I take AX minus lambda x equals 0, this is sort of nice, but I'm kind of stuck and I can't go anywhere until I do a silly thing, which is to stick in a copy of the identity matrix right here. Well, it's actually not silly, it's useful. It looks silly at first because you're like, okay, what all did you do? Well, what I did is I allowed it to be the case, or I allowed it to make it possible. Sorry, I made it possible to factor out the x. Now, at a prior step, that would not be possible because I can't just write a minus lambda times x equals 0 because this is nonsense. Because I'm talking about a matrix minus a number, so that's garbage. Okay. So I stick in an identity matrix and I look at this. Okay. Now, so the original equation, the eigenequation that we're trying to solve, is equivalent to this one. And when I look at this one, I remember, in order to find an eigenvector, eigenvectors are non-zero vectors. I want a non-trivial solution to this equation right here. How is it possible to have a non-trivial solution to a homogeneous equation? Because that's exactly what we've got, right? We've got matrix times vector equals 0. So that's a homogeneous equation. Well, from our characterization of invertibility theorem, we know that the only way that you can have non-zero solutions to a homogeneous equation is when that matrix is not invertible. And that matrix is not invertible precisely when its determinant is 0. Okay. So now I have an equation of numbers, as opposed to in the previous step where I had an equation of matrices, like a whole system of equations. So that's much more difficult. So all of a sudden, things just got simpler. And that's the beauty of determinants. And that's more or less the whole reason why we talk about determinants in this class. So, okay, so this is called, actually here, let me write officially, like the characteristic polynomial. Of A is this expression. And so if you remember, the formula for the determinant makes the determinant into a polynomial into its entries. So the formula for the determinant, if you were to write out the whole gory thing, it's going to be a sum of products of aij's with each other. So it's going to be a polynomial with like a whole, n times n different variables, right? And the characteristic equation is when we set this sucker equal to 0. And so since we can only have solutions, non-trivial vector solutions of this original eigenequation, when we have zeros of this equation, lambdas, which are zeros of this equation right here, so roots of this one, we see that the eigenvalues are precisely the roots of the characteristic polynomial. So the solution strategy, how do we solve this actual equation? What we do is we find the eigenvalues oh well. As roots of the characteristic equation, or sorry, characteristic polynomial. And then once we have those, for each eigenvalue that we've discovered, we compute the eigenvector by row reduction. Right, because we're at this point, we're back to solving this, where are we? This one right here, solving this one. So how do you solve this equation? Well, once you know what lambda is, you just have matrix times x equals 0. So what do? You row reduce the augmented system, but it's homogeneous, so forget that column of zeros. So you're just row reducing a minus lambda I. Okay.